So in today's session, we'll be considering a revision on arithmetic progression and geometric progression. So what I'll first start with is obviously the first sum. So it says if Tn equal to 2n minus 4, find the common difference. So you might ask me whether it is a sum on arithmetic progression or geometric progression. So you see the sum says, or the sum asks us to find the common difference. Now, if you remember, common difference is a rule of arithmetic progression, whereas common ratio is a rule of geometric progression. So when I see this common difference term included in the sum, I can essentially deduct or deduce rather that the sum is based on arithmetic progression. So they have given me the general form of the arithmetic progression. Now this general form of this arithmetic progression, it can be used to find specific terms of the arithmetic progression. So whatever value of n I put here in basically on both sides of this expression, I can get that term. So using this, I can essentially get any term of the arithmetic progression that I want. And that is essentially what I will be doing. So you see, I first found out the first term of arithmetic progression. So I have essentially put n equal to 1 on both sides of this expression, and I get t1 equal to 2 into 1 minus 4. So that gives me 2 minus 4, which is minus 2. Again, I put n equal to 2 in the general form of this arithmetic progression, and what I get is t2. I've replaced n with 2, equal to 2 into 2 minus 4. So that's 4 minus 4, which is essentially 0. Now why did I do this? If you remember the definition of common difference is the difference between the second and the first term, or the third and the second term. Essentially, it's the common difference between any two consecutive terms. So you can find essentially any two consecutive terms. You can find the fifth and the sixth term. You can find the 700th and 701th sum term in the progression as well. But of course, the first and the second term is easiest to do because they require the least number of calculations. So I have found the first term and the second term, and what I'll do is I'll just subtract the first term from the second term. So what I've done is the common difference is equal to t2 minus t1 equals 0, minus of minus 2 equals 0, plus 2, because there were two minuses, so it gets cancelled, and it gives me 0 plus 2, and that's what essentially I have. So common difference is equal to 2. So that's the first sum done. Next sum is, they have told us that a1, a2, and it goes on. So I have some dots here, if you can see. So a1, a2, up to some the series, they are in AP. And they have said that A8 plus A10 equal to 24. And I need to find A9. So they have given me A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, and so on are in AP. Now, if you remember the concept of arithmetic progression and arithmetic mean, you might remember that the condition said if X, Y, and Z are in arithmetic progression, then Y is said to be the arithmetic mean of X and Z, and Y is given by X plus Z by 2. So if we have three numbers which are in AP, then the number in the middle is said to be the arithmetic mean of the number on both sides, and it's given by the half of the sum of the numbers on both the sides. So that is the condition that we'll essentially be using in this sum. So by the sum, A8, A9, A10 are in arithmetic progression. So this part of the condition is met already. So that means A9 can essentially be regarded as the arithmetic mean of A8 and A10. And if that is the case, which is true in fact, A9 can be expressed as A8 plus A10 by 2. That is the formula or the expression for arithmetic mean. Now we essentially have been given the value of A8 plus A10, which is equal to 24 as per the sum. So what I've done is I have replaced A8 plus A10 with 24. And the number 2 on the denominator remains there as obvious. So what I have is A9 equals 24 by 2, which is 12. So I have used the condition of arithmetic mean and arithmetic progression in this sum to find a particular value of A9, or to find a particular value of the nth term of this arithmetic progression. So the arithmetic mean formula is a really important one, which you need to remember. Okay, so we have the third sum here. So in a GP series, T5 and T3 equals, T5 is to T3 equals 7 is to 9. We are required to find T9 is to T5. So they haven't given me any rules of the geometric progression. They haven't given me A, they haven't given me R. So they have given me neither the first term or the common ratio. So let's assume what we don't have. So I assume that the first term is A. So let me just write the general form here first. So I have Tn equals A r to the power n minus 1. Pardon my dangerous handwriting though. So we have Tn equal to A r to the power n minus 1. Again, if you note that the number of the term that we consider, the exponential of r is 1 minus that. So it's one less of the term that we are considering. So going by that assumption, or going by that rule, we have T9 equal to A r to the power 8, where A is the first term of the GP series that we have considered, and R is the common ratio. So it's the ratio between the second and the first term, or the ratio between the third and the second term, and so on. We have discussed it in details in the geometric progression session, so you can have a look at it. So we have T9 equal to A r to the power 9 minus 1, because it's n minus 1. So it's A r to the power 8. T5 equal to A r to the power 4, and T3 equal to A r squared. So these three are the terms that we need, or the terms that we are interested in based on the sum that we have. So these are the three terms. Now what they have given us is T5 is to T3 equal to 7 is to 9. So that is essentially what I'll try to deduce what I have from that. So I have T5 by T3 equal to 7 by 9 as per the sum. Next, what I do is I replace T5 with AR to the power 4. That's the general form of the GP series, or general form of the basically the fifth term of the GP series. And I replace the third term with its general form AR squared. So I have AR to the power 4 by AR square equals 7 by 9. So if I cancel out A on both the numerator and the denominator, and if I cancel out R square on both the numerator and denominator, I'm essentially left with R square equals 7 by 9. Let me just write this 2 in, yeah. So we have R square equal to 7 by 9. So that is what has been given to me by the sum. This is a condition that was hidden in the sum. So you see this condition T5 by T3, it doesn't seem like they have given me either A or R, but if I simplify this, they have essentially given me the value of the common ratio. So sometimes we need to just solve or simplify what they have given us, and then we'll find that they have given us a very, very important condition or a very important rule of the sum. So now I have R square equal to 7 by 9. Next, we move on to what has been asked to find. So we find out T9 is to T5. What we do again is, like the previous part of the sum, I replace T9 with AR to the power 8, and I replace T5 with AR to the power 4. So if I need to find the value of T9 by T5, I can again find the value of AR to the power 8 by AR to the power 4, because they are essentially the same. I cancel out A on both sides, and let me reduce the exponential of R as well. So if I need to find the value of T9 by T5, I can also find the value of R4, R to the power 4. Now this R to the power 4, this can be written as R square whole squared. So if you remember the law of indices, if you want, I can always discuss it later. So if I use this expression R square whole squared, then I can use the value of R square that I had previously found out, and I replace R square with 7 by 9 and squared, of course. So it's R fourth equal to R square squared equal to 7 by 9 squared. And with just pure multiplication or squaring, I get 49 by 81. So I have T9 by T5 equals 49 by 81, and that's what they have asked us to find. So sometimes there are conditions that are hidden in the sum, and we need to solve the sum or solve what has been given in the sum, and we find the condition that they have given us hidden in the sum. So let's do the last sum for today. Express 2.025, where 25s are decimal. So it's 2.025252525, and it goes on as a rational number. So what I first do is I express it in non-decimal, like a non-recurring form. So this is a recurring number. So 2.02525252525, and it goes on till infinity. Now you might be wondering, why am I doing this sum in an arithmetic progression and geometric progression sum? You will find out that this is essentially an expression of infinite geometric progression sum. So because this goes on to infinity. Now, if you write this term in this way, so we have 2 plus 0.025 plus 0.0025 plus 0.000025. If you add these few terms, you will find this expression. And I have put plus infinity, so the terms succeeding these will cover this part of the sum, rather this part of the recurring part. So what I have is essentially an arithmetic, an infinite geometric progression. So I represent 0.025 as 25 by 10 cube, and this part as 25 by 10 to the power 5, and this part as 25 by 10 to the power 7. Now I write 2 separately, and what I do is this part, I take it as an infinite arithmetic progression, the infinite geometric progression. So by definition, this is my A, this is my first term of the infinite geometric progression, and that is what I use in this expression. So it's A. Next, R, as we know, is the ratio of the easiest way would be the ratio of the second term and the first term. So we have 25 by 10 to the power 5 by 25 by 10 to the power 3. If you do the calculations, we get R equal to 1 by 10 square. So that's the R, that's the common ratio of the infinite geometric progression. So those are the 2 rules that we have for this infinite geometric progression. Next, I use the expression for the sum of infinite geometric progression. So it's A by 1 minus R, and I essentially put the value from this from these values that I had found out, and I just use pure calculations, and I find the value to be 401 by 198. So this is the rational form of expression of 2.025 recurring. So if you use the calculator, you may check that if I divide 401 by 198, it will give me 2.025252525.